you for coming, everybody, to this is the first session of the summer 2019 ESIP meeting. This one is titled Big Gridded Data. It's basically a look back and a look to where we are and where we're maybe going with quote unquote big gridded data. We were going to call it something more like spatiotemporal data cubes or something like this, but we wanted to be a little more inclusive and maybe evocative of a bigger picture. So big gridded data was the topic that Rich Signell was largely responsible for. So he's one of our speakers coming up. So we have, I think, 4 or 5 speakers. We're hoping to do this something of a lightning talk. So brief talks that are kind of hitting the high points of some previous and ongoing work in this space. And then we're going to have quite a bit of time for discussion and kind of interaction among the group here. I hate traveling to these meetings and just getting talked at and then going home without having had a chance to interact. So let's try and make this pretty interactive. So the speakers that are in the room, if you guys can come up and do your song and dance, and then probably just stay up toward the front of the room. I don't think we need to fill in the table here. We can have a conversation after this is all done in a fairly fluid fashion. And I will ask that if we are asking questions, you can try to use a mic. There is a group of 6 or so online right now. So we have a few people remote that are trying to listen in and take part. So thanks for coming along, and let's get started. All right, so I'm going to ask each person to kind of introduce themselves, but before their talk and kind of their background and why they're presenting here. So I'm Dave Blodgett. I've been working with the U.S. Geological Survey in the water mission area for going on 10 years now. And when I started, I started with this project that we call the Geodata Portal, and it's a system to provide big gridded data to landscape modelers. So down sampling spatiotemporal data to polygon basis for driving environmental models. So that's where I've been working in this space for a while, and I just kind of want to introduce the session here with a very broad overview of the transition that we've seen happen over the last 10 years or so, and probably nowhere more significantly this transition has happened in storage, right? So we've seen the just price per gigabyte of a hard drive drop precipitously, and that seems to be tailing off, which is interesting. The cost of storage has gone from this, you got to buy a big storage device periodically to increase your storage capacity, to you can kind of pay as you go as you need it on the cloud, which has some changes in the economics of storage. We've seen more and more object storage that is capable of parallel I/O, where in the past our kind of storage area or our WAN connected spinning disk storage wasn't as suited to these parallel workflows that we now kind of do regularly with remote sensing and other big gridded data. And we're just seeing this potential for deployment of terabyte scale to petabyte scale science data become normal, right? This isn't unique anymore. It's not just a few data centers around the landscape. It's pretty much anybody with the money can do this and scale it up and turn it all off if they want to at the end of the day, which is really changing the game. Okay, so we're also seeing a transition from largely server-based, doing a lot of work at a central compute facility to downsample or render or whatever it is, the data you're interested in technologies like grads or threads, to a much more serverless architecture where you're depending on the way you're storing data, say in an object store, to provide you the subsetting and the access to data that you then pay the compute to render and do work with on say a cluster in the cloud. So these technologies like Stack which is just a way to expose a collection of data that's stored more or less as objects to a client, or ZAR, which is a way to chunk up or introduces a technology to chunk up big gridded data into an object store and make it accessible via kind of parallel I/O. You know, these serverless technologies are much less functional than the server technologies, but they open up a whole realm of flexible opportunities for us. And another tier that I like to think about, because this is kind of where I've worked for a lot of my career, is this idea of a service client that sits at the data center, right? So Giovanni or the Geodata portal fill this niche of it's software deployed on shared architecture, shared infrastructure, and has the ability to interact with big data services for a user on kind of high throughput systems that have direct access to the data or very close access to the data. And they do a bunch of work for you and pass you the data that you actually want, right? But we're moving into this world where instead of those big built systems, and maybe not instead of, but in addition to those big built systems that solve problems for users, we see these systems like Jupyter notebooks with access to big data stores, right, in cloud hosted environments. We're seeing things like Google Earth Engine, where they're loading large amounts of data onto a system that you can go in and write a script against. You know, the Pangeo project is essentially doing the same thing, where they're pursuing the ability to have very flexible workflows against very highly parallelizable storage, with the ability to spin up lots of compute on the fly for custom workflows. Totally not a possibility in these easier to use potentially, but more limited systems like we've built. And the two that I give as examples here are Giovanni and the Geodata portal, but there's a slew of them that implement these kind of processing workflows that are hardened up and are very performant and easy to use, but don't give you the flexibility that you get from these things like Jupyter Hub. ArcGIS Online is a similar one. You can deploy your process to ArcGIS Online against data that's hosted in their cloud, right? And we're seeing this more and more as the way that we're going to do these workflows. And that's having implications on our modeling. I would go so far as to say that the modeling is a little bit behind, or a little bit, it's poised to do a lot of work given those new technologies, but our big models are just kind of starting to come along. And you know, NLDAS has been around forever, and it has the potential in the next little while to totally change the way it works with regard to the big gridded data that it both reads and writes. And that's an area I'm hopeful that we can see some progress in the not too distant future, because getting forcings for models that are generated from NLDAS is currently not real great. But if we were to say have NLDAS write out to ZAR and be available via Pangeo, ta-da, we've got this huge potential to do environmental modeling that we didn't before. And so in the past, we've had these things like CMIP 3, CMIP 5, where it's just delivering a huge amount of netCDF content to a big file store that's available via threads maybe. And where's that going, right? What are we going to do for the next climate model intercomparison? I'm not actually familiar. I'd be curious to have a little conversation here with people that do know where we're going with that with regard to these technologies. I put this because this was just a momentous thing with the new dynamical core that was deployed into the GFS. You know, that's new model code in a model that hasn't changed for a long time. And it's a big deal that we're seeing that evolution, that we're actually seeing change in that space, right? And the one that's near and dear to my heart, because I've worked on it very closely, is this thing called the National Water Model. We're seeing terrestrial modeling and the potential of different kinds of big gridded data. Watershed time series type data come into this arena. And where are we going to go with that more topologically structured, less gridded in a rectilinear sense, but topologically structured gridded time series data in this space? I think that's an interesting question. Okay, so what's next? There's a technology that a lot of the quote unquote big boys are using, labeled property graphs, right? That we haven't really gotten any penetration in the kind of Earth systems modeling world yet. And it encompasses what we think of as semantic web data, it is also able to be, you can consider a property graph a coverage. You could, so in watershed modeling, the network of watersheds, which is a grid, it's a coverage of the landscape that you can think of as a grid. It's also a connected property graph. And many of our models have that characteristic. It's a grid that's also a property graph because the elements of the grid connect to each other in a graph. And there's a ton of power there. So how do we leverage that? Is there potential there for kind of future technologies, future capabilities that get at some of these integrations that we really want? We've got these new technologies that are just coming online. The W3C, data on the web best practices, have been around for a little while, but we've got systems that need to mature into those best practices, and they're going to open up all kinds of potential. Things like Stack, right? This is evolving really rapidly under our feet, and it's really exciting to see where it might go. And the last thing I'll leave you with, and this actually is kind of in reference to a parallel track that's happening with this session, and that's this idea of moving the big gridded data to the edge, right? And this is a reference to edge computing, right? We have cell phones that are capable of doing machine learning algorithms and AI algorithms on video that they're recording in real time. So say we move that kind of a capability to a drone that's collecting, a terabyte of imagery a day, and only sending back a few kilobytes of really interesting information. What's the implication for the data that we're collecting? What's the implication for the models that we run? How do we reconcile the kind of three-dimensional gridded data that we're collecting from systems like drones with the more typical big gridded data that we think of as kind of XYZT models, right? That are the bread and butter that we've been working with for so long. There's a lot of interesting potential there, but a lot of really kind of tricky problems to reconcile. So there's a big, I would encourage, after this session, I would encourage people to check out the Drone API conversation, because I think there's going to be a lot of really interesting stuff happening in that space, because that technology is becoming so ubiquitous, and the potential of technologies that are being driven, say for self-driving cars, et cetera, it's going to open up all kinds of things. We have zero idea of what they're going to be, but I guarantee you're all going to want to be on the ground floor of that when it starts to take off. So that's what I have, and I will turn it over to Charles, to introduce himself and take us into the next talk. So, and let's hold questions and conversation for the end, but please do jot down questions and ideas for conversation as you think of them, and we'll come back to them. So, cool. Thank you, Charles. Yeah.
All right, so as for what I'm called, I usually go by Charles. And when I don't go by Charles, I usually go by Chuck. And the way I pick it is Charles is a prince, Chuck is a famous pilot, and Charlie is some kid who can't play baseball. So anyway, NCEI's service of big gridded data through the Nomads project and through our climate data on records, or CDR's climate data records, has been pretty conventional. We tend to use NetCDF for the stuff we produce. A lot of the model data that we display goes through Weather Service, and they like Grib. And we use threads to do some of the basic stuff. We have LAS, we have some custom web applications that like Climate at a Glance that use threads as a source. And then a lot of people just download the data wholesale or file by file with FTP. Well, all this is okay, but as things move, there's some things that are kind of important. First of all, Nessus has this sort of cloud first thing going on where they want us to migrate some things to the cloud. And then the big thing is that on the cloud, object storage like S3 is much cheaper, often by a factor of more than 10 than block storage. So for example, Amazon has S3, they have Glacier, which is the cheapest. S3 is the cheapest online. They have block storage connected to one of their virtual machines, which is limited to one machine and more expensive than S3. And then they have their shared block storage, which is the most deluxe, gold-plated, expensive storage you can get. And meanwhile, in our server room, our IT folks have informed me that setting up a big object store is a lot easier and less expensive for the performance and storage space than setting up a big block storage system. So most of our data management and server code uses block storage. The FTP and HTTP, you can put that on object storage pretty easily, but I mean, put that on object storage pretty easily. But Threads, for the most part, uses block storage, or at least the version we have, and that's how we use it. We've experimented with object storage, but it's been suboptimal so far. So what do we do about it? Another thing about Threads is that Threads, OurTap, and our custom applications is people can ask our computers to do a lot of processing. So for the Nomads project, there's this service called NetCDF subset service, which doesn't seem all that complicated, but we had to limit the number of connections doing it to prevent people from causing the poor Nomad server to crash. So those are the issues that push us towards change. So some solutions. Oh wait, here's the back. Yeah. Threads itself may actually get object store built into it. It seems like Unidata is moving in that direction. And then, of course, another thing is, as he had alluded to in his thing, putting the data out there in a format that's easy to subset and work with in the first place. And I mentioned ZAR, N5, which is very similar to ZAR, and cloud optimized. Those are good for data of all types. And then cloud optimized GeoTIFF, which is good for image, geo-rectified images and such. And all these basically, the load falls on the client, but they can get a lot of features similar to the web mapping service that Threads does or the NetCDF subset service. And then, of course, loading these things, the sort of shell scripts and stuff and Python and Java that we've been using to load on block storage has to be object-based. And also we have a new inventory system, which is called Kafka, and that works on sort of a workflow, it's inventory manager. It's based on Kafka that goes through a workflow management system. And so Apache NiFi is good for managing workflows of data, and it's very cloud capable. It has S3 functionality built right into it. And then Kafka is useful for keeping track of things, message passing, and it's for metadata. And those two are built to interoperate. So on that side, the Kafka and NiFi can work beautifully together to replace our sort of more cobbled together block storage based things. And so that comes up to the issue of ZAR. And ZAR is nice because in NetCDF, you have a NetCDF or you have a bunch of NetCDFs. And if you have a humongous NetCDF, it doesn't work very well. And if you try to combine NetCDFs in something we call an aggregation in Threads, and it's troublesome enough, sometimes I call them aggravations, that imposes a lot of work, and the server has to have big amounts of cache, and having lots of those can run a Thread server out of memory and make us have to reboot it every night, and so on. The thing about ZAR is it's built so that because it's chunks with metadata pointing to all the chunks, a library adding to it or reading from it doesn't have to do a whole lot of work and keep a whole lot of it in memory. So when we add to an ever increasingly large, say, ZAR file that is one of our climate data records from start to end, when we append, we just add files at the end. And furthermore, there's client libraries so that there's a good chance that people will just go read the client, our library, our data, instead of using one of our services that uses our CPU. So to try this out, I did something called a ZARTApp. And what ZARTApp does is I could say, hey, we're going to use ZAR, but I'd have to have some way of demoing it. So I needed a ZAR client. And the ZAR client is the simple thing that basically will read a ZAR file, and I picked one of our more noteworthy data sets, the NOAA global temperature, which is sort of the global climate change record. And so what OurTap does, and it's actually running, and I could demo it later, is you tell it what part of the data you want in terms of which variable and which indexes of the data, time, depth, lat, lon, and it returns JSON that shows the data. So, and JSON isn't that great for a demo. I needed some graphs, and a lot of people like to use spreadsheets. So I wrote spreadsheet scripts that can query OurTap and get JSON and put those into the cells of a spreadsheet, which led to these graphs. So the line graph of OurTap data, that is the temperature anomaly, in other words, deviation of temperature from the mean, near New Orleans for a great big period of time, 1970 to about now. And on the right, what you see is a recent global anomaly of the whole world for a recent time, like I think July 1st or so. And the red dots are where it's warmer than normal, and the blue dots are where it's cooler than normal, and the size of the dot depends on how far it deviates from the mean. And these were done in Google Sheets using my OurTap client library. Now, OurTap's a demo. It had to be simple, so that's why it's only using JavaScript, but more usefully, it could be an OpenDAP server, which would allow us to do our aggregations as ZAR and our files as ZAR. And in the case of this data, the data gets converted to NetCDF. That's not its original form, so we could simply have a conversion to ZAR as part of it. And there's another one that I've experimented with, OISST, which they want to reprocess from NetCDF and that's to NetCDF4, NetCDF3, and it starts life as a sort of very generic binary that they refine into something more useful, and that process, again, could go straight to ZAR. And so if we had something like OurTap that lets people conveniently use our data, but guides them to learning how to use it themselves without having to run stuff off of our own servers, that leads us to a future where we have a much more scalable and less burdensome system. Any questions? I have my computer set up to do demos, so if anyone wants to see it in action, I can show them. But that's later on. All right.
Ed.
Okay, howdy folks, I'm Ed Armstrong from the NASA Jet Propulsion Laboratory, and I'm going to talk about a tiled storage technology for ocean data access analytics. This is the Oceanworks project. We actually introduced the capabilities of Oceanworks and the technology behind it, Nexus. Over the last 2 summer meetings, there was a demonstration run by Frank Raguska and Thomas Wong. So I'm not going to dive too in the nitty gritty. Hopefully the technology is somewhat familiar to you, but I will give you like a brief overview, and then the direction where it's currently being taken and adapted to in the physical oceanography DAC where I work at. So again, I'm up here speaking on behalf of a long list of developers and contributors, too many to list right here. So Oceanworks was a NASA AIST project. It's kind of wrapping up. We're actually having our final review this week. And it's about enabling a next generation ocean science tools and services with data analytics and services. We're doing things like oceanographic anomaly detection, sea level rise and variation, observing hydrological mass change. Also, there's an in situ to the satellite matchup component of this project and ocean models that's work in project. Now the software or the technology behind this this capability is called Nexus. It doesn't really stand for anything. It's just the brand name we've given to the capability. But essentially, it's a tiled storage database based on both Cassandra and in our case Solar, with an analytics portion that's handled by Apache Spark. The entire software stack actually is an open source project. I'll have another slide on that, but it's the integrated ocean science data analytics platform. And all these capabilities that we've built into Nexus and Oceanworks and its sub projects are all these RESTful accessible or accessible via RESTful APIs. So they work very friendly in things like Jupyter notebooks. Actually, the key message that was kind of left off here is that we want to be able to harmonize data, tools, and services, or this is a capability that allows us to harmonize data, tools, and services so that scientists can concentrate on the data and getting research results on the data versus data preparation and data conditioning, right? So that's one of still the big bottlenecks of working with the big data is that the scientist often has to prepare the data before they do the analysis. All right, so not too much on this side other than that kind of just shows some of our architecture allowing us that from a design standpoint that allows us to do large data ingest as well as parallel processing in this kind of 2 database architecture philosophy here. One database, the Cassandra, that does the chunking, right, where we essentially break up the grids into smaller chunks and then index those chunks in another database in Solar that contains also metadata about those chunks. Some semi-analytics that we collect on those chunks with regards to data variance and the data mean and other properties. Nexus is a pluggable architecture. We've focused on a few technologies. I've mentioned Apache Cassandra. First of all, the way where you deploy this is you can deploy it in a number of ways. You can deploy it to your own cluster, your own private cloud, or we've demonstrated to deploying it to Amazon Web Services. So this is we've designed this and Dockerized and containerized the software stack so it can really be deployed everywhere. I've mentioned Apache Cassandra as the the science database where we store the chunks, but we've also demonstrated that you can use a ScyllaDB and Amazon Simple Storage Service. I've also mentioned the Apache Spark as the underlying data analytics capability, but Amazon Elastic MapReduce and Amazon Athena can also be utilized. Okay, going on. So I did mention this is a open source project, right? Blessed by the Apache Foundation, and so this whole software stack you can find on a NASA GitHub site. Download it. It's nicely containerized and Dockerized. That you can install into your system and be up and running in a very short amount of time. We will be at the ApacheCon in September with some representation from somebody. I'm not sure exactly who's going to be at the project, but again, the key message here is all the development we've done, all the capabilities we've done, and the software stack is all available in the open source community, to the open source community. Okay, so I mentioned that we're essentially, you can interact with Nexus with any programming language. I mentioned Python and via Jupyter notebooks, but here's a simple example of like using IDL, a few lines of IDL to make a simple call and download a very nice SST time series. This actually demonstrates the North American SST blob. Probably some of you who live around here are familiar with that term, but it was a large, almost continual warming event in the North Pacific. And so we're using IDL and just a few lines of IDL code here and this little graphic demonstrates actually when I did this, I was in a conference in Europe, and so just connecting back to the server at JPL that houses all the data and generating this simple plot in essentially a few seconds. So some of the Nexus integration points that are success stories, there's an Oceanworks portal at JPL is one example of the integration of the Nexus technology. So that's directly from this Oceanworks AIST project, but there's been several other examples too. There's a NASA sea level portal, and for exploring and creating data analytics from altimeter data, looking at sea level rise and variation. Then also the GRACE portal, where we're looking at mass changes from the GRACE and the GRACE follow-on data. And there's others in progress. So one of the things, I work in the PODAC, and we've been working on this task of integrating the Nexus technology as the back end to our SOTO visualization tool. So SOTO is a state of the ocean, is a visualization tool, has many different oceanographic layers in there, allows the user to quickly peruse satellite oceanographic data, some of it actually quite long time series data. We have data going all the way back to the origins of the oceanographic satellite records, so the early 1980s. From SST, and in the 90s from ocean topography, and this is all can be visualized, but of course they're just static images. I mean, you can move around, click and zoom, and click and get the data value points, but you can't do any kind of time series analysis. So integrating the Nexus technologies allows us then to provide the user with data analytics to be able to do time series analysis with a number of different plots. So let's look at some of that quickly, just that functionality. So here's an example of a few screen grabs in the user interface that's provided to the user. So essentially they're picking a region and they're picking this chart capability, and they're picking the different layers that they can interact with. Right now, they're just limited to 2 layers. So you have a primary layer and a secondary layer. And then you create these charts and do things like time series analysis. So this just shows like a nice view here of an oceanographic phenomena called upwelling in the Gulf of Tehuantepec off Mexico, where you have a lot of these gap winds coming over there, blowing through this narrow valley through Mexico to the Pacific side, and then causing cooling on the Pacific side. So you see this is an example of the SST drop in SSTs in that region of interest. You see that cool blob of SST there. And the plot shows nicely the wind in red. This comes from the MEDOP instruments, and the SST in blue. That's the Mirror SST. That's a gap-free level 4 data set. And nicely shows when the spike there in mid-December of winds there, and you see the nice correlation there with the SST drop. So this is the mean, but of course you can look at things like the mean, the max, the count, or the standard deviation, the variance, a number of different metrics in this time series analysis. So that's just time series. We can do Hofmöller plots. This just shows the trade winds now, where you see the intensification of the trade winds to the north of the equator, intertropical convergence zone, and then other things like El Nino warming. These are again like Hofmöller plots here, where in this case we're looking over zonal bands at specific latitude bands across the entire zonal box there and longitude, and plotting the values there. In this case, it's latitude, and this shows again just the time average of the blob. So I think I'll wrap up right there. We've had some nice introduction here from Dave about some of the problems. Increasingly, we're talking about gridded, but you have to throw in there ungridded. So this particular technology is primarily working with gridded data, but we do have some examples of where we've taken level 2 data. So we do have some examples of working ungridded data. And, it's going to require technology that harmonize data tools. So I'm coming back to this theme again of, harmonizing tool services and computation resources so the scientists can sorry for that little typo there, but they can concentrate on getting results, science results versus data conditioning and preparation. So there's a number of technologies that can, they're trying to tackle this, including Nexus. Nexus has demonstrated some successful deployment now in the sea level portal, the NASA Sea Level portal and the GRACE portal, and we've run into a few kind of like technology and performance hiccups of trying to get it going into the PODAC, into the SOTO visualization tool, but we'll solve those soon, and we'll hopefully recruit some of you folks. We're doing some beta testing. So that's it. Thank you. Okay, we get the next speaker up here, which is Rich.
All right, I'm going to kind of piggyback on this theme here, talking about making big gridded data fair, the approach that has been being used in IUSE, which I've been participating in for some time. I'm a physical oceanographer at the U.S. Geological Survey in Woods Hole, and my bosses have allowed me to sort of just participate in IUSE to help out any way I can, but specifically with the gridded data, because my background is as a coastal ocean modeler. So just one little word about IUSE. There's 11 different regional associations in IUSE, 17 different federal agencies. It's led by NOAA, but it's not a NOAA thing. And my contributions are a USGS contribution to IUSE. In each one of these regions, there's a bunch of different models running, a bunch of different sensors in the water. It might be federal, it might be state, or it might be academic, and they need to be able to put all that data together. It's really, I kind of view this as like a little microcosm of what ESIP is all about, right? Like people from all these different institutions collecting similar kinds of sensor data and model output and we need to be able to somehow harmonize all this stuff. And US IUSE feeds into the international GIOS as well. So, the data we have a lot of model output, and the model output is not raster data. It's not regularly spaced in general. It has these funny like vertical coordinates, like stretched from the surface of the ocean. They actually go up and down as the sea level goes up and down. And on the right, you see this sort of curvilinear grid. This is a small Massachusetts Bay grid, but it's definitely not regularly spaced, right? So to actually make this interoperable, we use these CF conventions. A lot of you probably heard about them, but this is an example of what a variable temperature would look like on that grid. Okay, so we have this floating point variable temperature with some dimensions, and then it has these attributes, right? Like standard name, seawater potential temperature. That is a standard name that's maintained by the CF organization, cfconventions.org. There at the bottom is the URL. There's acceptable units, and then it specifies the coordinates, which mentions these other variables. And if you look at one of those variables, like the vertical coordinate, you see that it has a long name and a standard name. That standard name actually points you toward an equation that you need to use to calculate the vertical coordinates. So it's pretty complicated. But what all that stuff allows you to do is then take different models. So like on the left of this, so this is the overall sort of existing architecture plot for IUSE. On the left, you see all these models, ROMs, NCOM, HICOM, Selfie, all these different models that can be harmonized by the use of those CF conventions. So you can write software then that doesn't know anything about a particular model, but will be able to access any one of these models. Now, the people who distribute these models usually don't pay a whole lot of, sometimes they do, but sometimes they don't pay attention to the CF conventions. And so the Threads data server, which we've already talked about a bit, makes it very convenient for you to add these attributes to basically standardize them on the server side, behind the scenes. And then you have this common access layer being this common data model in the Threads data server. And that then allows you to serve out standardized OpenDAP. I would say standardized by having CF conventions, so OpenDAP with CF conventions. But we can also, for sensor data, we can serve it out as sensor observation service. And most importantly, perhaps, well, not most importantly, but we can also, through the NC ISO service, generate ISO metadata. So it provides that ISO metadata can then go into a catalog. The catalog can be searched. And then we can and have this something like this IUSE catalog. So IUSE, the program, has about 14K data sets. It uses CCAN and PyCSW to provide the standardized catalog services. So you can go here, you can go to this little GUI and look for data, or you can do it programmatically through the CSW interface. And then what that allows you to do then is to do things like create a notebook here that is running, actually this is running on Binder, so anybody can launch this notebook and do this for themselves on the cloud without installing anything in their browser. And what it does is it starts off with a catalog search. It looks for a particular geographic region and a particular time extent and particular variable type, in this case temperature. It finds all the sensor data from all the different organizations, pulls that through SOS, and then it finds all the models that are running in this region, and it pulls and it actually interpolates the model output using those conventions. It knows how to do that and comes back with time series at each one of those places where we had data. And then the user in the browser in this notebook is able to zoom in on a map, select a station, click on it, and to get a pop-up like this that shows the model output over 4 different models overlaid with the sensor data. This was never able to be done before. Nobody had even compared these models because it was so difficult to try to understand all the different model coordinate systems and all that kind of stuff. So it's very powerful. So this makes these workflows reusable. And so now, in the last year or so, and this is kind of paralleling what Dave was talking about, I've been working on this Pangeo project, and there we have data sitting on the cloud in ZAR, and we're accessing it with this parallel framework in Python using Dask, and Xarray is providing this NetCDF model. So we don't have NetCDF anymore, and we don't have Threads anymore. We don't have OpenDAP anymore in this system. We don't have any services, as Dave was talking about, except for the S3 service. But the whole concept is basically the same. And in fact, the CF conventions become even more important to be provided with the data in the containers. So with the data sets, we don't have the, we can't just fix it on the service side. So we want to fix it actually at the bucket level. But the nice thing about ZAR data is actually the metadata and all those attributes is in JSON, so it's very easy for the provider to do. They don't have to rewrite any of their data. So this is just an example of what this looks like, and this is going to be sort of an advertisement for later sessions. But this is just one of these dashboards where we have 40 all those blue lines in the upper right there are different cores reading ZAR data chunks, processing them, and making this calculation that in this case the maximum water level for Hurricane Ike, and then you can zoom in the browser and see increasing resolution as the data gets re-rasterized. You can do the whole, you can do everything on the cloud using just your browser. So and the hope is in the future, I think that I certainly hope that we have all of our model output, all our sensor data on the cloud, in some cloud, and that we're able to connect through very high-speed networks. And so in that sense, the data will be data proximate, and we'll all be do work much more efficiently, effectively, and it'll be more reproducible. So I think the interesting thing here is that even though we're not using some of those technologies, the whole concept just all works better with the cloud, but we have some work to do. So right now, as I mentioned, we can use S3 direct access instead of these data services, so we don't get bogged down with data services or the service actually being down, as Charles mentioned. There's going to be some cloud data optimization sessions this afternoon where we're going to kind of explore the data-friendly cloud formats. The data sets, as I mentioned, need to be standardized at this at the S3 level, and then we have to generate ISO record. Well, in this framework, we have to generate ISO records from that. So we need some tool to generate the ISO records from those data sets, because the ones we have now are pointing at OpenDAP endpoints and or NetCDF files. And then we need to put more data and more workflows on the cloud. And in that regard, there's going to be a Pangeo Jupyter Hub session after lunch, like a hands-on session where you can play with this stuff and watch your own dashboard crunching bunches of data on the cloud. And then there's going to be a scalable data proximate computing session tomorrow afternoon where folks are going to talk about Pangeo and other approaches to do the same kind of workflow. So with that's it. Thanks.
Good morning, can you hear me? Okay, sounds good. My name's Mike Riley, and I'm the PI on the Styr project. Styr is supported by the Access program. Styr stands for Spatiotemporal Adaptive Resolution Encoding, and it's a way of dealing with the variety that we have in earth science data, and also a way of dealing with the volume. My background is I have about 25 years in high performance computing, modeling, and simulation. For the past 5 years, about the past 5 years, I've been working with some earth scientists. Quo is the fellow who came up with some of the basic ideas about how to encode location and try to bring different kinds of data together. We also of note, we have UCSB and OpenDAP involved. One of the things that we'd like to do is to be able to have some of this encoding and the benefits that you get from encoding occur transparently to the end user. So it might be part of the information infrastructure. You don't even know it, but you're still getting the benefit from it. Robert Wolf from NASA Goddard Space Flight Center is looking over our shoulder in part of this, and we have a couple of collaborators at NASA LARC, John Curry and Jeff Walters. So my goal here today is just to describe a little bit about the project, what we're trying to do. So one of the big problems that you have lots of different kinds of data that you want to bring together to answer an earth science problem. However, each of these different kinds of data has its own native format, you might say, and they don't always line up. So you have to do some sort of regridding or interpolation to bring them together. And even before that, just in order to find the different pieces of data on your wherever you have them stored and then bring them together, that's another step as well. And with our encoding, we try to make that much better. So different kinds of data, couple different kinds of grid simulation, swath, point. And with our encoding, we provide a universal framework to bring all those together. So let's see, let's bring some of these together. All right, so this just gives you a visual for what I was mentioning before. If you see the index, let's see, okay, is this a laser here? Okay. No, it doesn't matter. You see these index M and L, the grid each has its own native indexing through the data set. Same thing for swath, and then point, that can be just about anywhere. Somehow you have to reconcile all these together in order to make them comparable. And that's a big problem to a scientist who doesn't want to spend all of his life just moving data around. So what we want to do with the Styr encoding, and Styr has both spatial and temporal. The spatial one is perhaps a bit more interesting. What we do is that we have a recursive subdivision of the sphere, and then as we go and cut up the sphere into different triangles, we label which triangles we take down as we recurse down. And doing so, we build up essentially a map or a set of directions down through the tree, down to the point that you're actually trying to encode. And so this number here, this Styr index for the spatial part, is just telling you where in your tree of subdivisions of the Earth's surface that you're going, and that gives you a number. Now the adaptive resolution piece in there tells us that what we do there is that we encode inside this number a rough area size. So not only do you have a geolocation in this number, you also have an area. And that helps you when it comes to trying to figure out intersections and overlaps and trying to represent more interesting regions on the surface of the Earth, for example, like a drainage basin. So we have this encoding of a tree structure, a tree partitioning of the Earth's surface, and from that we get a number. And so for any particular number, for any particular position that you have on the Earth, we can give you a number corresponding to that Styr index for that location. And depending upon how big the thing is that you want to be talking about, that gets put into the number as well. And again, the point of this slide is just to highlight that it's an encoding. It's an encoding of the position. So if you want to have latitude and longitude, that's one kind of encoding. And if you're doing it in single point precision, well, there's the numbers right there for a particular case. The corresponding Styr spatial index is just underneath there. And the area information for that particular one is the level 20th of the traversal down the tree. That corresponds to about a 10 meter area. So here's an example. We just divide up the surface of the Earth. We start with a root polygon, in this case an octahedron, project that out to the surface of the Earth, and then we just divide each of those triangles by 4 recursively, and just figure out where you are in particular triangle at a particular level. Now, one of the things that we do to deal with the volume of the situation, each one of these colors over here corresponds to a chunking, for example, onto a particular storage asset. So if you have 16 servers or something like that, and you assign parts of that tree to each one of these servers. And so in real life, what you'd do is that you'd actually be using smaller chunks spread over a larger number of degrees of say servers in the cloud, for example. But this is a way to actually co-align data from different sources onto compute assets that are close to each other. And so the hope here is that you're going to minimize the amount of data communication that you have to have, and you'll be able to parallelize the different sorts of intersections and comparisons that you want to do with your science data. And for an example over here, this is swath data, which has been indexed using Styr, And this just shows you how it lines up and how it actually gets divided up, parallelized across those 16 resources. Now, we heard a lot earlier about grids, and grids are kind of strange. You know, they're kind of complicated. You have to use, for curvilinear case, you have an equation which you have to refer to. And so here, just a couple of examples that come from the model and simulation community. You have the cube sphere on the left. On the right, you have the icosahedral at a particular level. Down below, you have the ever popular lat long, which is mostly used to look at and understand the data that you're trying to answer questions about. And the point here is that in order to compare two different kinds of data set, you're going to be, for example, if it's ungridded, you're going to have to be transforming that ungridded data onto the grid, for example, onto the lat long. And then if you want to move it to, say, a modeled simulation, you're going to have to interpolate or extrapolate that data from one grid to another. And that's just the regridding process that you probably heard about before. Now, you might be thinking that with all our triangles there and our tree structure defined on that, could you use our Styr index as a grid? And I guess you could. We don't do that. We're more interested in indexing the different kinds of data and the way that they're arranged and providing a uniform way to bring that data together so that you could then regrid it to a common grid. Styr could be that common grid, but that's not where we're going with this particular access proposal or work. An idea, just to give you an idea of the sort of things that you can do over here, the blue swath going across this screen over here is a trim swath. And behind that, indexed in red triangles, is the NMQ radar data. And so you have two very different kinds of data set. One's a grid, one's swath, both indexed using Styr, the hierarchical triangular mesh. And then you do a very quick comparison because you're just dealing with numbers here, integers. You can do the intersection very quickly over here because you already have everything indexed using these sets of integers. The light green that you have there shows you where you have the NMQ and the trim data intersecting. And then the next thing you can do, for example, is that you can say, well, depending upon where my trim data is a certain value, I want the NMQ data from that. And it all goes very quickly. It scales because we have that tree structure defined. We have it distributed across parallel assets, and all this can go on very quickly, scalable in both volume and variety. So the updates, the Styr project started last year. We're coming up and finishing up our first year. We have a new simplified API. So we're getting through the basics here. Temporal indexing has been the big thing happening at the beginning of this year. We wanted our temporal approach to be good enough so that we could handle intersecting spacecraft data. There's a new Python interface which might be interesting to a number of people. And we're taking baby steps to put this in as a function in the back end of OpenDAP so that you can provide queries to the OpenDAP, but then OpenDAP on the back end uses the Styr to do things in parallel, dealing with both variety and volume there. So next steps, we're building out the functionality. Again, we're halfway through the 2-year project, and we're looking to work with partners and community to try to exercise this and help people see the benefits. So there we have it. Very good. Speaking next, we have Jay Su. All right.
Thank you, Mike. Not only you introduce me, but also you introduce the regrading subsetting part. I'm Jay. I'm from NASA JS and we have a lot of people working for this project. And Jay, of course, Benita, Carly in the audience, Hualan, Su-Hong, Dana, and others. And we also have many people attending this session remotely. So today's talk is about L34RS, a level 3 for regreader and a subsetter for Earth grid data. So you may know that JSDisk has a popular tool called Giovanni. So how many of you have heard of that? About half, shy. So how many of you have heard level 3 for regreader and a subsetter before? Really? Thank you everyone. Seriously, so actually it's a true story. So last AGU meeting, I met a friend from University of Maryland. He is working on NLDAS data, which is in GRIP, and he want to convert that to NetCDF4. So he actually did it in a kind of not efficient way. So I asked him, do you know we have a tool called L34RS? No. So I guess that's the reason I'm here to introduce this tool. So for this tool, we have a subsetting function for mirror, for example, mirror 2. This is a kind of older statistics, but it's generally the same for last year. You can see that over 30 million files were subsetted and saved more than 95% of volume in both in space or time. And for L3 for RS for the LDAS data, and it was launched in December 2017, and you can see quickly get populated and get a huge download files. So the unit is in terabytes. What products we are supporting? So we're supporting Mirror, Mirror 2, FLDAS, GLDAS, NLDAS, of course, NCL, LDAS, OMI, and in this month, GPM. So if you want to have any subsetted data or regret data, you can look at them from the JSDisk website. So some highlights. It's user-friendly. Here's a barcode if you want to take a picture. You can see we can select lat long, variable, grid, and of course you can select different interpretation methods. And the grid can be defined by the tool. So here's the different integration methods. It's not complete, but I think most of them are popular ones. And these are grids. You can see this, many of them have standard name. And if you want to add one, it's very easy. We just add one or several lines of code. So actually, another true story about this is if you see the last one, GFDL, actually one friend from Nova, they are interested in comparing Mirror 2 data with GFDL data. So what's the quickest way to do that? The answer is through L34RS. So basically, you go to the JSDisk website. This one, if you remember, then choose the metadata you want to regrid or subsetting, and choose the grid GFDL. Then you get the output file in GFDL format, grid. Recently, actually it's not recently, last year, several of my colleagues visiting a conference in Hawaii, and they got the volcano eruption. So actually one of them is in the audience. So if you want to study this by OMI product, SO2 variable, and you want to compare from other products like Mirror 2, so first you can regrid this OMI product to to Mirror 2. Then you can take a daily mean, since metadata are 3 hourly. So take a daily mean of metadata also provided by level 3 for IS tool. So use this single tool, you convert convert two products to one single grid, and you can compare them. You can see what happened and what's going on there. And for level 3 4IS, we also have powerful data handling of input and outputs. So now we are supporting NetCDF4, HDF4, HDF5, HDF EOS5, grip data, ASCII data, COC data. I think someone mentioned that before. And actually, I changed my slide. We decide we will move to ZAR maybe in the future, since for obvious reasons mentioned by Rich and Charles, others. So I think that's the end of the talk. Yeah. Thanks.
All right, so that is the end of our kind of formal set of talks here. I have a couple of questions from Jeff DLB online. I have a few as well, but why don't we start if there's folks in the room that want to get the conversation started. Do we have any hands?
Yeah, hi, I'm Ken Casey. I'm from NOAA's National Centers for Environmental Information. I remember we're supposed to introduce ourselves, right? Thank you, yeah, +1. And one of the big things I'm working on now is getting NOAA's archives and even more broadly, our data into the cloud. So we're trying to build a whole new enterprise system. So all of this stuff that has just been presented is really, really very timely. And the more I think about it, I think the way you laid it out in your intro slides there, Dave, is this potential transition from server-based to serverless approaches to enabling all this wonderful data interoperability and subsetting and so forth. And so I think and I'm kind of thinking out loud here, so I'll get to a question in a minute, but like Charles laid out a really nice and very straightforward example of a serverless approach to do some basic things, and Rich showed like some more complicated things, but also still serverless. And I think what I'm trying to get to is sort of maybe the I don't know if it's the counter, because I don't want to couch it as a versus sort of thing, but like folks, like Ethan and is Gallagher here in the room? Who coming from the more traditional serverless side of things, what their thoughts are about this sort of potential transition to a serverless world.
I tried to get Ethan to give a talk, but he declined. So maybe this is Ethan's opportunity to get a word in edgewise.
Hi, Ethan Davis at Unidata at UCAR. Yeah, well, we've been talking a lot about serverless threads, serverless thread server. Okay, well, maybe not call it that, but using the cloud technologies to take advantage of all the cloudy platform and have it serverless. And I still think that's probably something that needs to happen and move forward with. And I think ZAR is definitely a cool thing. And NetCDF, we're moving forward with implementing support for that in the NetCDF libraries, C and Java. I'm a little curious about, like Rich said, getting rid of the servers or not using ZAR, and then you don't need anything else, any of the server interfaces, web APIs, I don't know. And that, but of course Nexus kind of goes the other way, and it's all server, it's a microservice-y cloud serverless-ish, or going to potentially moving in that direction. So I'm really curious about that but and Rich is going to say something.
I just want to clarify. I wasn't trying to advocate for abolishing services. I was just, I think it's cool that you don't have to have like if you want to just get the data, you don't necessarily need a service. But lots of people may still want to have a service, but you could build it on top of that, right? So I think that's, there's all sorts of reasons to have services still, but it allows a lot more innovation when you can go right to the data as well. So.
I guess I was going to say a lot of the same thing as Rich said. It's sort of like, it's not serverless, it's more like I could say server optional. And also to distinguish, the term serverless often gets used in the cloud world as meaning a function as a service, which is a different concept. And what I was proposing for NCEI is the idea that even if you have a service, if you can keep it as simple as possible and prevent it from having a heavy burden on your systems, but still have it as convenient for the user as possible, then that's as good as not having to run any heavy servers. So we would have an OpenApp server, and since I guess Unidata guy could tell me more about the plans, and NetCDF is going to support ZAR. So I presume that means that Threads could support ZAR. But the idea is that the user has the option of using a client library to do all their graphing or using a service. So it's sort of like a server optional thing. As for my ZARDApp demo being serverless and the function as a service thing, I sort of designed it to be that way. I suppose you could, I don't know how, I guess Threads' Java function as a service version of Threads could exist, I suppose. So, so to the Threads Unidata representative, what are the plans on making Threads deal with ZAR?
So yeah, I'll leave. There are other questions in the room, but I'll leave it up to you all to.
What are plans for Threads to support ZAR? Well, our current plan is that the NetCDF Java library will support ZAR, reading ZAR data and writing in the not too distant future. And that would feed into certainly Threads being able to do stuff with that data and serve it and aggregate it and do whatever. And yeah.
But the configuration details are going to be a work in progress for some time, right?
Configuration of?
Well, I mean, the way you configure file-based Threads data sets now is going to be a little different when we go to a ZAR basis, right?
Well, there's still a data set that you reference.
Sure.
So I think
so. It doesn't. So you're saying it doesn't really break the NCML semantics?
Well, I don't know about the NCML, but it doesn't break the notion of a data set.
Sure. Okay. Cool.
I think the bigger question is, or another question is, how do we deal with aggregating large collections of ZAR data sets?
Yeah. So, cool. Chris?
Chris Linus from NASA. So I just wanted to pull back a little bit on this conversation. I think it's a really useful one to have, but I think there's a place for both, this sort of direct access and the service-based access. So for instance, the direct access works really well if you're in the same cloud, for instance, as the data. One thing we have to remember is, we all might be using, let's say, AWS, but if you also want to bring in data from, say, Google Cloud, or particularly the Europeans tend to like other, smaller clouds. And that makes the service-based approach it's a little bit more tractable in that case. Now, I am funding James Gallagher, so if James isn't here, I'm funding Gallagher's work on the Hyrax flavor of OpenApp and making that work in the cloud with fine-grained access. And one of the interesting things we found about that is that when you open that up to do fine-grained access, and it's based on this DMR++ thing they've got, it also can optimize the way that you access these data aggregations that we used to make through NCML. So it actually opens up some new possibilities in highly performant aggregation across data sets, even when you didn't create the data set to be that way.
Yeah, I don't remember who made the comment, but something more or less along the lines of how ZAR opens up, or just Object Store in general opens up the potential for massive aggregations in a way that we couldn't do in the past because of parallel IO and kind of the realities of metadata about objects. I think that we shouldn't overlook that kind of shift, right? Because we're going to a place where every data set is a collection of objects that are kind of a virtual data set, regardless of size. And anyways, it's cool.
Yeah, this is Mike Riley again, working with the Styr project. With regard to the aggregation of very large numbers of data sets, one of the ideas that we've been kicking around is using something like a file system structure or naming convention for some of the files based on the Styr index, so that you have this tree structure built into the name and structure of the files or file systems that you have. And that might be one way that we could speed up some of the interaction that you have when querying against and aggregating large numbers of file sets.
I just wanted to say about aggregations in Czar. I mean, Czar does allow for a lot of things and may be great for aggregating some data sets. One of the issues with aggregating data sets just using dimensions is that it's really fragile to any variation, any non-homogeneities in the data collections of data sets, which are very common out there. And when you get large collections of data sets coming in, especially if it's operational, feeding in from operational things. So, and that's why the NCML aggregation is very fragile, is because it's based on in the thread server is based on coordinates. Dimensions.
Yep.
What some of the newer aggregations in threads is doing is looking at the coordinate systems and building on top of those. So trying to allow for that flexibility.
Yeah.
Anyway, so I think that's where I'm curious about how the cloud and Czar, and then going beyond that to aggregations that aren't just array-based, because Czar is array-based chunking.
Yeah.
So those chunks are aggregated together, just like an HDF5 file, the chunks, they're aggregated together based on the dimensions, not coordinate systems.
So maybe this is a good time to turn to one of Jeff's questions for Ed. And it's this: do you have any comments on chunks in Cassandra and indexing in Solar versus chunks in S3 objects as in Czar? And I'm also really interested in this idea of do we chunk and index in real space rather than in index space? And is there a connection to things like discrete global grids, which seems a lot like what Michael was talking about. So yeah.
I can't comment specifically to Jeff's question there. With regards to Cassandra versus S3 object. I know we've done some work with S3 like indexing directly into S3, but I see Frank in the room. I was going to maybe pass the buck to him and have him comment, because he's a little bit more apprised on the actual technology, what we've done there. So I'm more on the application side. So Frank actually led one of the demos at past ESIP workshop. So.
Yeah. So in terms of, I guess, chunking in Cassandra and indexing in Solar versus chunking in S3, I mean, the main difference, technologically speaking, that I see is in Cassandra, when we're indexing these chunks, we have to index them just straight as blobs. Cassandra doesn't have support for, or great support for, like a multi-dimensional array data type. So what that limits us to in Cassandra is they recommend only 1 megabyte blobs maximum. So from a technical perspective, that's a hard limitation that you don't want to go over. Whereas with S3 objects, I mean, they can be as big as you want. Also, being able to store the data directly into like a Czar format in an S3 object is going to make it a lot easier, because like I mentioned, in Cassandra, it has to be stored as a blob. So there's serialization and deserialization that has to happen there to put it in and take it out of Cassandra, where you won't have that cost in S3. So that's a couple of things off the top of my head.
Cool. Okay, good answer, Frank. And I hope that answered your question, Jeff. Or is there more discussion on this topic?
Yep.
So I'm Robert Wolf from NASA Goddard. I guess it is. Okay, so one of the challenges I think we have with big data is that everything's not in the same grid, and in many cases it's not gridded at all with some of the level 2 data or point data or so on. Okay, so That's better. Okay. So you have data in different grids. You have data that may or may not be in grids, swath data and point data. One of the things that I've been working with Mike on is, how to bring those two data sets together. I don't think we're quite there yet. There was some talk about Nexus having that capability in the future, but maybe we could talk a little bit more about the challenges of that area, of that, and how do we, a lot of assumptions the users make in terms of gridding and so on is actually, the real challenge is actually getting the data into a common grid so you can actually do your analytics on it. And so what can we do as a community to make that possible?
Somebody want to take that? I think Rich, or I guess I'd be happy to speculate, but there's probably better people in the room.
So I'm Dave Fulker, and I think that the point about crossing the boundary between gridded and non-gridded data or various types of gridding is among the most important reasons in my mind why it's a little bit unfortunate to try to move in the direction of the terminology service or serverless or serviceless or something like that, because it seems to me my use of that term service has to do with the abstractions that are associated with it, and so the fact that a particular realization of a service might impose some obstacles to getting to the data has to do with the nature of the abstractions that are used in that case. And it seems to me that some of the work described here in the Styr and the other ways of looking at how one moves among various types of grids and non-gridded data is the way to the future. And I suspect that it's the sort of the abstractions of how you actually utilize those access methods, which in my mind are a form of service, is actually where the future lies.
Yeah, actually, I just wanted to comment, maybe it kind of follows on that. Actually, I just wanted to, if I gave the impression, or if anybody else did, that that only grids, gridded data benefit from, sitting in object storage, it's definitely not the case. I mean, I'm looking at streamflow data, and as long as it has a coordinate, as long as it can be fit in something like an HDF file or ZAR file, it has the potential to be accessed directly in a performant way, just by being on object storage. So it's basically anything you can stick in a file.
I've seen a lot of miscellaneously gridded data stored in threads, and so what usually people think of as a lat long or curvilinear grid, where they're actually arranged in a grid, but it's all just arrays. So I would see things like this FVCOM model has nodes and edges that connect the nodes, and you would have an array that describes the nodes and an array that describes the edges, and they're a grid technically. And in a situation like ZAR, what would happen is it would just chunk along these sort of linear arrays as opposed to a two-dimensional, but it would still chunk, it would still go into S3, and it would still be efficient to extract and subset the data. You just have to use more sophisticated subsetting algorithms.
Right. It seems like to an extent, this serverless quote unquote approach is actually more about exposing low-level access to the data in a way that we couldn't when we were mounting hard drives to servers. And since we're not mounting hard drives to servers, all of a sudden we can provide that low-level access to the data sustainably at some level. And that's not necessarily going to be applicable in all use cases. So anyways, there's definitely still a role for the server side client, right? That can do regridding and do the hard work that needs to be done for certain use cases. But anyways, it's fascinating. So I want to turn to another one of Jeff's questions, which is for Mike, saying, can you use Styr to index just particular features, e.g. a path followed by a hurricane, or for machine learning purposes? And I would extend that a little bit to ask about kind of how this, well, yeah, so go with that question first, and I have a follow-up question for you.
Do we have? Yes, there we go. The hurricane track is actually an interesting one because we put together a conceptual graph showing just that idea for a presentation last year, where we actually took some data about the path of the hurricane and the size of it, and we actually made a three-dimensional chart, three-dimensional visualization, using the Styr triangles that we had there, tracking it along over a map. So yes, you can do that. The Styr, what happens is that if for any sort of arbitrary region that you have on the surface of the Earth, for example, what you would do is that you could simply find a covering set of triangles that cover that, and then each of those triangles has a number. And so you can actually convert that arbitrary region to either a set of integers or a set of integer intervals. And you can go to town with that.
So the follow-up question is, this is really kind of unrelated, but specific to Styr. How does your approach with Styr relate to the discrete global grid approach that's been brought forward by folks from Australia and seems to be catching on?
That's something that's come up in recent discussions, and we're still studying that. Okay. From my initial reading of that, it seems that we should spend some time essentially recasting or describing Styr in terms of DGGS terminology, and then it would be clear what the connection is.
Yeah, I mean,
perhaps somebody here with a bit more experience might help me with that.
Well, that's a perfect answer for what I was wondering, kind of where you were at with the parallel evolution of the two things, because they share, conceptually they share a lot, but I think from a purpose perspective they're a little different. So.
This is Quill. I'm a designer of the original designer of Styr. So as far as I know, the DGGS currently does not have resolution information associated with the grid system. I think that is currently what I see the biggest difference between Styr and the DGGS. But on the other side, the Styr, the branching, the qualification, and that part is very similar to a lot of the DGGS systems we have.
So conceptually, they're pretty similar, yeah.
So I don't have the answer, I just have another question. They were comparing Styr to other grids, and one of them was the icosahedral grid, and what that, I'm guessing that is that you have an icosahedron and then you subdivide its triangles into little triforces just like Styr. Is Styr related to that? I mean, do they share, I mean, what's the difference between Styr and the icosahedral grid? Is it what I described, or?
Thank you for that question. I'm not an expert in the icosahedral grid. I have not worked with it, and perhaps somebody here has a better understanding of that. But what happens with Styr is optimized for the underlying geometry for figuring out whether a point lies on a particular inside a particular triangle or something of that nature. So it's not been optimized for doing things like approximation, making sure that every triangle has exactly the same size at a particular level. That's not what it's aimed to do. Its aim is to try to come up with an efficient way to locate objects on the unit sphere. So that's fundamentally what's going on with the spatial part of the indexing.
Sorry to jump in again, and icosahedral grid is very similar. I mean, Styr and the icosahedral is very similar. The only difference is that in the branching, we started with an octahedron, and then they started with a icosahedron. Okay, then the other thing is that for the icosahedral grid that people use is in simulation, like the CSU group using model simulations. They also aggregate into hexagons mostly, and then except for 12 pentagons. Okay, and then we talked about that too. And the problem is that once you have to aggregate, you break the hierarchical structure, the natural hierarchical structure that, of the original branching. The original branching, you basically branch it into, in the octahedron case, you branch into 8 quadtrees. And in the icosahedron, I think it was 20 quadtrees. So you break that hierarchical nature of, once you have to aggregate, you break that hierarchical nature, which is a very, very nice property when we have to use it for, like denoting the adaptive resolution and also in the set operations.
Interesting.
Yeah, the Styr is nice in that it's efficient. It's triangles all the way down, so the calculations are very nice in that way. But for example, if you want to be doing aggregate statistics over Styr, you actually have a distribution of triangle scales at any particular level, whereas other folks, for example, from the modeling simulation community, so they spend more time trying to figure out how to have triangles of good properties for the particular simulation. So that's a different situation that you have there.
So we have a few more minutes. Another question?
I also actually had a Styr question. I've always wondered, does Styr deal with different ellipsoids or different geospatial projections?
We could deal with those, but that's going to be a matter of future work, right? One way to put it is that Styr provides a partitioning of solid angle. Okay, so we put ellipsoid around that, we'll be able to index it.
So it's just to clarify on the icosahedral, it's sort of like the minimum polygons of that can be hexagons and pentagons instead of triangles. That's another big difference, right? And also a Styr globe would make one heck of a construction toy.
So I think we're at break. Yeah. Well, thank you, everybody. This session turned out as well as I could have hoped, and I hope you all enjoyed it and got something out of it, and a little bit of discussion was useful. And definitely look up the speakers if you want to continue the conversation or get a demo or anything. So thank you very much.